Hello everyone, now we are going to do the experiment on heat exchanger. The theory part as well as classification related to the heat exchangers already explained in the online classes. The students please go through those classes. Now I am going to show how to conduct this experiment. Okay. In your syllabus, the parallel and counterflow heat exchangers are included. This is an example for concentric heat exchanger. Concentric tube heat exchanger means that there are two tubes having a concentric. Here you can see that this is the inside tube and outside tube will be there. In the outside tube the hot water will be flowing, in the inside tube the cold water is moving. Here we can see that this is the inlet section. What? The cold water inlet section. This is the thermocouple to measure the cold water inlet, and this is the hot water inlet section. This is the thermocouple to measure at the temperature, that is hot water inlet, and this is the geyser where we are getting the hot water. Later come to here, this is the hot water outlet and corresponding thermocouple, and this is the cold water outlet corresponding thermocouple, and outside the pipe it is completely insulated. There is no any heat transfer takes place from the heat exchanger, only the heat transfer takes place inside the heat exchanger. Okay, here you can see the experimental setup here. For the parallel flow and counter flow, the parallel flow heat exchanger means the hot water entering and the cold water entering both are in the same direction. That one you are going to call as the parallel flow heat exchangers. Both the hot water and cold water, they are moving in the same direction. And finally both are exit at this end. The hot water will be exit in this end and cold water will be exit at this end. For this experimental setup, this knob, this valve should be in this direction, not in this direction. Both the valves should be in this direction. If both the valves are in this direction, then that is the parallel flow heat exchanger. Suppose the hot water is entering in this direction, hot water is entering from right to the left, and the cold water is entering from right to the left. That one you are going to call as the counterflow heat exchanger. For this experimental setup, both the valves should be in this direction. This is the main experimental setup in this experiment. First we will conduct the experiment on parallel flow heat exchanger. While you conducting the parallel flow heat exchanger, here you can see the water flow rate for the cold water and water flow rate for the hot water. The rotameter is there to measure the flow rate. First you have to set the water flow rate in both the rotameter as the same. Here you can see for the cold water flow I set it as 2 liters per minute, 2 LPM is there here, and the same thing for the hot water also I set it as 2 LPM and leave for some time so that the experiment come to a steady state condition. After that one we will conduct the experiment. First we are going to conducting the parallel flow heat exchanger. The same thing I am noting all the datas here, and the panel is here. Here you can see the cold water diameter means inside pipe inner diameter is 11 mm, outer diameter of inner pipe is 13 mm, and length of the cold water tube hot water diameter 34 mm. The D knot, outer pipe of the D knot is not required for our calculation. The length of hot water tube is 1.5 meter. So we have to consider L is equals to 1.5 and T1 is the room temperature. Here you can see here T2 and T3. Hot water inlet temperature, hot water outlet temperature. T2 means this is the thermocouple, hot water inlet temperature, and T3 is hot water outlet temperature. Next, here you can see T4 is the cold water inlet and T5 is the cold water outlet. For which condition? for the parallel flow condition. For the parallel flow condition, T4 is this one. This one, that is cold water inlet, and the T5 cold water outlet for the parallel flow condition. For the counterflow condition, because in the counterflow condition what happens, the cold water is entering here and exiting at that end. So therefore this T5 become cold water inlet. This T5 become cold water inlet in the counterflow direction, and this opposite end, that becomes the cold water outlet for the counterflow condition. This temperature you should know based on your experiment. For the parallel flow, T4 is the cold water inlet and T5 is the cold water outlet. For the counterflow heat exchanger, the temperature becomes the inverse. That is, T4 becomes cold water outlet, T5 becomes cold water inlet. Already 15 minutes is over. Now we are going to take the readings. Okay, we will start taking the reading. T1 is the room temperature. I will take it as 20, and flow rate is 2 LPM. T2 and T3 I will take. T2 is 46, T3 is 32. 46, 32. Next, we are conducting the parallel flow, and the flow rate is also the same thing, that is 2 LPM. Then T4 and T5. T4 is what? Cold water inlet, 18. T5 is 22. 18 and 22. The remaining unknown things we have to be calculated. Now the readings related to the parallel flow heat exchanger is over. Next is related to the counterflow. I already explained, to conduct the counterflow heat exchanger, just you turn this valve in this direction, that's all. Now automatically the cold water will be start moving from this end and leaving at this end. So the hot water is moving this direction, the cold water is moving the opposite direction. So this flow type heat exchanger is going to call as the counterflow heat exchanger. Now we will leave some 10 minutes, later we will take the data. Okay, around 10 minutes I left out to get the steady state condition. Once again we will start taking the readings related to the counterflow heat exchanger. The T1 will be the same thing, the room temperature for the counterflow, 20. Flow rate will be the same thing, I have not changed for hot water side as well as the cold water side. Now we will check it out. What about the T2 and T3? T2 is 50 and T3 is 33. T2 is 50, T3 is 33, and we will note down the T4. Now the T4 is what? T4 for the counterflow is, T4 is cold water outlet, 17. T4 is 24. And the T5 is 17. Right now we note down all the data. Next we will show how to do the calculation of these two experiments. In this experiment the equations are available in the manual. Just you have to substitute the things and obtain the answer, that's all. The remaining calculation I will show now. Okay, now we will start the calculation of the heat exchanger for the parallel flow heat exchanger. Just I transfer all the data taken in front of the experiment. Just I transfer to one more sheet to do for the calculations. Okay, these are the data I taken from the experiment. Now we will calculate, the first one is the rate of heat transfer. The rate of heat transfer can be calculated by Q is equals to m dot H, specific heat of water, and temperature difference. That is what, this is the equation. M dot H CPW THI minus TH naught, that is equals to M dot C CPC TC naught minus TCI. Any one of these two equation we can find out the rate of heat transfer Q. Now I am using this equation to obtain the Q. M dot H is already taken from the experiment, that is 2 lpm, and specific heat of water is 4200. THI and TH naught is already is there. THI and TH naught means hot water inlet and hot water outlet. This is the hot water side. T2 means inlet, T3 is the outlet. So hot water inlet, hot water outlet, that is THI minus TH naught. Just I substitute the values, and the same thing I can return, this one is what, in place of THI and THI minus TH naught, THI minus THI, I can write T2 minus T3, and for the TC naught minus TCI. TC naught means cold water outlet, that is cold water outlet is T5, and inlet is T4, T5 minus T4, or this one, any one of the equation you can be wrote. This is for your understanding purpose I written this one. Next I will substitute the values. 2 by 60, 2 by 60 because the flow rate is in the LPM, 2 liters per minute. So to convert to a kg per second, you have to divide by 60, and specific heat of water is 4200 joule per kg Kelvin, and you substitute the temperatures THI, that is 46 minus 32. So we obtain Q is equals to 1960 watt. After calculating the rate of heat transfer, the next step is to find out the logarithmic mean temperature difference. For that one, this is the equation. This derivation already I given in the notes, and also explained in the YouTube classes, online classes. This LMTD is this is the equation: hot water inlet minus cold water inlet minus of hot water outlet minus cold water outlet, then ln of THI minus TCI, TH naught minus TC naught. From our experiment, what is meant by THI? THI is T2 and TCI is the T4. Those things I just I written here. The same thing I written here. What are the values will be there? Those things I substituted here. The hot water inlet 46 minus cold water inlet 18. 46 minus 18, that is 28. Next, TH naught minus TC naught, hot water outlet T3, and cold water outlet 32 minus 22, that is 10 degree. The same thing I written here. I simplified, and the LMTD is 17.48 degrees centigrade. Next is overall heat transfer coefficient, that is what, based on inner diameter UI, based on the inner diameter UI. UI is equals to Q into AI into LMTD. In the experiment already we saw that there are concentric tubes. One is the inner pipe, and outer is the outer pipe, outside is the outer pipe. In the inner pipe the cold water is moving, in the outside of the inner pipe, and in the inner pipe the hot water is moving. These things already we saw in the experimental setup. This diameter you should be take, this diameter, inner diameter of the inner pipe di, that is the specification is given in the data hand in the manual, that is 11 mm, that is also mentioned on the experimental setup panel. So you substitute the AI, you find out pi into di into L, pi into di into L, where L I taken as the 1.5 meter. Substitute here, you will obtain the AI. Then you substitute AI Q LMTT to obtain the overall heat transfer coefficient based on the inner diameter. Finally I obtained, this is the value 2164.63 watt per meters per Kelvin. Then next, effectiveness can be calculated by Q max. This is the equation. So finally we obtained effectiveness for the parallel flow heat exchanger is 0.5. In the similar way, we will do the calculation for the counterflow heat exchangers. The data which are the taken from the experiment, the same thing I written here to do the calculation. First, we have to find out the rate of heat transfer, the same equation we are using here. And I substitute the values, that is Thi minus Th0 for the counterflow heat exchanger is 50 minus 33. I substitute here, I obtained as Q is equals to 2380 watts. After calculating the rate of heat transfer, the next is the LMTD, logarithmic mean temperature difference. Here the terms will be changes, that is what Thi minus Tc0 minus hot water outlet minus cold water inlet, and natural log of these above two ratios, the above two terms, and I will going to substitute the values, the Thi, Tc0, all those things. The Thi means 50 minus Tc0 is 24, 50 minus 24 is 26, and later Th0 33 minus cold water inlet Tci 33 minus 17, that is 16. So the same thing I obtained here and I substituted here. Finally I obtained LMTD as 20.6 degrees centigrade. After calculating LMTD, next we have to find out the overall heat transfer coefficient based on the inner diameter of the inner pipe. Inner diameter of the inner pipe, Ui is equals to Q divided by Ai into LMTD. Already you calculated Q. Ai is what? Already what the things studied in the last experiment, same thing, pi dIL. Substitute here, substitute the LMTD, you obtain Ui as 2230.38 watt per meter square Kelvin. Effectiveness is equals to Q by Q max, T2 minus T3 divided by T2 minus T4. Here effectiveness you obtain as 0.65. Later, after calculation, the next is what are the things you got, those things you should be substituted in the result. What is the overall heat transfer coefficient for the parallel heat flow heat exchanger is, for the parallel flow I obtained Ui is 2164.63 watt per meter square Kelvin, and the Q value I obtained as 1960 watt. Effectiveness is 0.5. In the same way, for the overall heat transfer coefficient I obtained for the counterflow heat exchanger is 2230.38 watt per meter square Kelvin. Heat transfer obtained is 2380 watt. And the final effectiveness is 0.65. 0.65. You can see here the effectiveness for the counterflow heat exchanger is more, 0.65 compared to the parallel flow 0.5, and heat transfer is also more compared to this one, and overall heat transfer coefficient, all these three values is more in the counterflow heat exchanger compared to the parallel flow heat exchanger. Therefore effectiveness and efficiency is more in counterflow compared to the parallel flow heat exchanger. Effectiveness is high, heat transfer is high, and Ui, overall heat transfer coefficient, is also high compared to the parallel flow heat exchanger. This is the end of the experiment on parallel flow and counterflow heat exchanger.